In this video, we're going to do 3 examples of integration using polar coordinates, and we're going to be repeatedly making use of this formula, which tells us how to evaluate an integral over a polar rectangle using polar coordinates. This region R is a polar rectangle. It can be described using polar coordinates as the set of all points r theta, such that theta is between alpha and beta, and r is between a and b. A region like this is called a polar rectangle. It looks like that. This is our formula for integration using polar coordinates. If we want to integrate a function f over this polar rectangle r, then this integral can be evaluated using this formula. Notice that x has been replaced with r cosine theta, y has been replaced with r sine theta, and then we have r dr d theta. In the first example, we want to integrate a function over this region here. This region is a polar rectangle. It could be written like this. If we use polar coordinates, then this region R is the set of all points r theta such that theta is between 0 and pi over 2, and r is between 1 and 3. This is a polar rectangle, and the integral that we want to evaluate is this integral, the integral of this function, sine of x squared plus y squared dA. Now, according to our formula for computing double integrals using polar coordinates, this is equal to the integral from 0 to pi over 2 of the integral from 1 to 3 of sine of, and now x is going to get replaced with r cosine theta, and y is going to get replaced with r sine of theta. And notice something important happens, something good happens. When we look at the expression x squared plus y squared, and we replace x with r cosine theta, and we replace y with r sine of theta, then what this becomes is r cosine theta squared plus r sine theta squared, and that is equal to r squared times cosine squared theta plus sine squared theta. And we know from trig that cosine squared plus sine squared is 1, so this is just equal to r squared. So here we have just sine of r squared, and then we have r dr d theta. And this little fact, this little computation that we just did, it's worthwhile to internalize that. When you convert to polar coordinates, x squared plus y squared becomes r squared. That happens a lot in these types of problems. Okay, now we're ready to evaluate our integral. Let's do the inner integral first. To evaluate this inner integral, we need an antiderivative of this function, sine of r squared times r. And here's an antiderivative. It's minus cosine of r squared over 2. You can check that this antiderivative is correct by just taking the derivative of this function with respect to r, use the chain rule, and you will observe that you get sine of r squared. If you don't see this antiderivative immediately, you can use u substitution to find an antiderivative of this function. This antiderivative comes from u substitution. Now we're going to evaluate this integral. We need to take our antiderivative and plug in the endpoints. So evaluate the antiderivative from 1 to 3. When we plug in 3 for r, we get minus cosine of 9 over 2. And when we plug in 1 for r, we get minus cosine of 1 over 2. So when we evaluate this inner integral, what we get is cosine of 1 minus cosine of 9 divided by 2. This is just a constant. Now, to do the outer integral, we're integrating this constant from 0 to pi over 2. So what happens when you integrate a constant? The answer is just that constant value multiplied by the length of the interval that you're integrating over. So what we get finally is pi over 2 multiplied by cosine of 1 minus cosine of 9 divided by 2. That is the final answer. In this example, we're going to integrate a function f over this region here, which is a semicircle. This region D is a polar rectangle. It can be described like this using polar coordinates. D is the set of all points r comma theta such that theta is in between minus pi over 2 and pi over 2, and r is in between 0 and 2. Our region D can be described like this using polar coordinates, so it's a polar rectangle. And the integral that we want to evaluate in this example is the integral over D of e to the minus x squared plus y squared dA. So let's evaluate this integral using our formula for doing integration using polar coordinates. According to that formula, this is equal to the integral from minus pi over 2 to pi over 2 of the integral from 0 to 2. And now I'm going to, what do we have to write here? X gets replaced with r cosine theta, and y gets replaced with r sine of theta, and x squared plus y squared becomes r squared. That's a common pattern that we've seen before. So we have e to the minus r squared, and then we have r dr d theta. Okay, so now this integral has been expressed as this iterated integral using our polar coordinates integration formula. So now let's evaluate this inner integral. We have to evaluate the integral from 0 to 2 of e to the minus r squared times r dr. To evaluate this integral, we need to find an antiderivative of this function that we're integrating. Here's an antiderivative, e to the minus r squared, should be a minus sign here, and then divided by 2. You can check that this is correct by just taking the derivative of this and using the chain rule. You can also obtain this formula by using u substitution. So let's take our antiderivative and evaluate it from 0 to 2. When we plug in 2 for r, we get minus e to the minus 4 over 2. And when we plug in 0 for r, we get minus 1 over 2. So this reduces to 1 half minus 1 half e to the minus 4. That's what the inner integral is equal to. Now that we've evaluated this inner integral and it turned out to be this constant, which does not depend on theta, we're ready to evaluate the outer integral. We have to integrate this constant value over this interval from minus pi over 2 to pi over 2. And what happens when you integrate a constant over an interval? The result is just the value of that constant multiplied by the length of the interval that you're integrating over. So what we get is this constant value, 1 minus e to the minus 4 over 2, multiplied by the length of the interval that we're integrating over. We're integrating from minus pi over 2 to pi over 2. The length of that interval is pi. So this is our final answer. In this final example, we're going to integrate a function f over this region R, which is highlighted in red. This region R can be described using polar coordinates as the set of all points r theta, such that theta is in between pi over 4 and pi over 2, and r is in between 1 and 2. This region R is a polar rectangle. And here's the function that we want to integrate. We want to do the integral over R of the function inverse tangent of y over x dA. And it looks like it might be quite difficult to evaluate this integral, but things are going to simplify very nicely when we use polar coordinates. So let's use our formula for integration using polar coordinates to evaluate this integral. According to that formula, this is equal to the integral from pi over 4 to pi over 2 of the integral from 1 to 2 of tangent inverse. Now y is going to get replaced with r sine theta, and x is going to get replaced with r cosine theta. And then we're going to have r dr d theta. Notice that the r's cancel out here, and we're left with sine of theta over cosine of theta, which is just tangent of theta. And then here we have inverse tangent. What is the inverse tangent of the tangent of theta? The answer is just theta. So the function that we're integrating here reduces very nicely. It simplifies very nicely. We're just integrating the function theta times r. Now let's do the inner integral. We need an antiderivative of the function theta times r with respect to r. Here's an antiderivative, theta times r squared over 2. Let's take this antiderivative and evaluate it from 1 to 2. When we plug in 2 for r squared, when we plug in 2 for r, we get 4 theta over 2, which is just 2 theta. And when we plug in 1 for r, we get theta over 2. So we end up with 3 theta over 2. So now let's do the outer integral. We have to integrate from, we're integrating from pi over 4 to pi over 2. And the function that we're integrating, we have discovered, is 3 times theta over 2. And we're integrating with respect to theta. So let's find an antiderivative of this function that we're integrating. Here's an antiderivative. It's 3 times theta squared over 4. And let's evaluate our antiderivative at the endpoints. So from pi over 4 to pi over 2. When we plug in pi over 2 for theta, then we're going to get 3 pi squared over 16. And when we plug in pi over 4 for theta, we're going to get 3 pi squared over 64. We can simplify this a bit. This is equal to 3 pi squared over 16 times 1 minus 1 over 4. And this is just 3/4. So what we end up with is 9 pi squared over 64. That's our final answer.